let's finish off this section on work with one more example that has to do with pumping fluids out of a tank. Right? So let's say we have a tank in the shape of an inverted circular cone. Right? So in other words, something like this. Right? With a height of 10 meters. So height of 10 meters. And the radius will be 4 meters. Right? That's the full size of the tank. And we're going to say this thing is filled with water to a height of 8 meters. So let's say that's about here. Right? So this extra distance here is 2 meters. Right? We want to take all this water that's below this line and pump it out the top. So how do we find out how much work is required to do that? Well, what we're going to do is, again, something pretty similar to what we did before. We're going to introduce a new coordinate here. That's going to be 0 at the top here and 10 at the bottom. So this will be sort of our x-axis, right? And what this represents here is, just like with the cable pulling example, the further down on this you go, the further up you have to be pumped out. All right? So what we need to do is, again, very similar to the last case. We need to find sort of the weight of each little segment here and find out, how much force is required to lift that weight up out of the cone. All right? So to do this, again, what we're going to do is partition this into a bunch of, let's see if that goes here, partition this into a bunch of little pieces again. Right? Each one of these have width delta x. All right? And then inside, let's do this. And what we're going to do is we're going to take this segment here and we're going to just approximate it as a cylinder. All right? Because we want to make life easy here. All right? And then we're going to say, well, in here, this has to be pumped a distance of xi star, right? This depth here will be xi star, and we need to pump it that far up. So in order to do that, we need to find out, well, what's the weight of this little cylindrical chunk here? All right, well, to do that, sorry, what we're going to do is say, all right, here's our cone. So what we need is we need the radius of the cylinder, right? We got the thickness, we need the radius. So to get that radius, right, let's see. So what I have here is xi star. So this height here is xi star, right? And this number here, this is ri. Let's call it ri for the ith radius. Or at the radius at this point. Right? And I know overall this is 10 and this is 4. So I can use our similar triangle arguments. Oh, sorry. Sorry. I need to measure this from the right spot here. So the distance from here to here is xi. So the distance from here to here is 10 minus xi star. Right? All right, we need to have that correct when we're doing similar triangles here. So we can do radius over, or this over this equals this over this. So ri over 10 minus xi star equals 4 over 10. And so if I solve this for the radius, we get, this is going to be 2/5 times 10 minus xi star. All right, so just standard similar triangle trick here. All right, so at a depth of xi star meters, this is how much there is left in the triangle. All right, so now that we have the radius, we can say the volume of that piece. So let's call this VI. This is 2/5. Oh, sorry. The volume is pi RI squared times the thickness, which is delta x. Okay. So here we have pi times 2/5 times 10 minus xi star quantity squared delta x. All right. That's great. So how do we, continue with this problem? So we have the volume of that chunk. What we need now is the weight of that chunk. So here I'm going to call this Fi because we're interested in the weight. We're interested in that as a force, right? That's the force due to gravity that we have to overcome to pump it out. So to get the force, which in this case is the weight, come on, right, which in this case is the weight, this is going to be density times volume, right? And the density here is 1,000 kilograms per cubic meter. So 1,000 kg per cubic meter times this here, which will be pi times, or let's do this, 4 pi over 25 times 10 minus xi star squared delta x. All right, so that's going to be our force. Or sorry, the mass. Sorry, I don't know why I said this is... I said that wrong. Sorry, this is mass. So we'll call this MI. Got a little ahead of myself there. Mass is density times volume. Now, using this, we can create the force due to gravity, which is the weight. So then, Fi, this here is the weight. Okay, this is mass times, here in this case, we want to write mass times acceleration due to gravity, which we'll call g. Okay. So I'll simplify some of the units here as well. So 1,000 divided by 25 times 4 is 160. So this is really 160 pi 10 minus xi star squared delta x. And then this is times g, which is, let's just leave it as g for now. Right? We are going to use g is, well, it's really approximately 9.8 meters per second squared. So we'll toss that in at the end. So now this force is sort of the weight of this chunk of water right here in the cone. Now we just multiply that by xi star because that's how far we have to lift it. And that gives us the work. So the work, Wi, this is work. This will be Fi times, let me use star here, times xi star. Right? So that will be, let's just toss this in the calculator now. 160 times 9.8. So it'll be 1568 pi 10 minus xi star squared delta x times xi star. Right? So this is the work required to lift this chunk of water right here in the cone all the way out. right? That's the work required to do it. Now we just have to integrate over the entire chunk of water here. All right? So we want to add up all these, which turns into an integral. So the work is going to be an integral of this stuff, where again, we replace the delta x with a dx and the xi stars with just an x. We're going to have 1568 pi times x times 10 minus x squared dx. Now the question is, well, what are the bounds on this? Well, we want to take, again, the very furthest part we have to pull or pump out to the very highest part we have to pump out. So the highest part is at a depth of 2 meters. The lowest part is at a depth of 10 meters. So we integrate from 2 to 10 here. Right? So this covers sort of, again, the smallest, the part with the least amount of work, to all the way down to the part with the most amount of work. So the shallowest to the deepest. Right? And now we just integrate this, which isn't a particularly interesting computation. So let's just pop this in Mathematica real quick. So we want to integrate 1568 pi x 10 minus x squared. We want to integrate this from 2 to 10. Right? And the exact answer here is 3,211,264 pi over 3. Probably not that enlightening. So let's get that numerical answer here. And this will be about 3.36 times 10 to the 6. What are our units here? Our units here are, in fact, in joules. All right. So quite a few joules. Actually, if I'm being really careful with my units, since I have 1 decimal precision here, probably round this to 3.4. 3.4 times 10 to the 6 joules. Right? Right. So again, that's about it for this. Hopefully that doesn't seem too bad. Again, the whole the whole point of these problems is you have to figure out what force you're sort of working with, and then, integrate that times the distance. Right? So with that, hopefully this made sense here, and see you in the problem sessions.